Good evening, everyone, and welcome. On behalf of National Anveshika Network of India, NANI, a unit of esteemed Indian Association of Physics Teachers, IAPT, and Shiksha Sopan, it is my pleasure to extend a warm welcome to all of you for tonight's webinar titled Calculus, a retrospective view on institution and result. This is Vimal Kumar. We are truly honored to have as our speaker this evening, Mr. Vaibhav Varun. Mr. Vaibhav Varun's background is a fascinating as it is accomplished. Originally from Darbhanga, Bihar, he spent a significant portion of his life in Moscow, Russia. There, he distinguished himself academically, graduating with a bachelor's degree in aeronautical engineering from the prestigious Moscow Aviation Institute, a true titan in the field, holding the distinction of being the only such institute across all the Europe and Asia. But Mr. Varun's talents extend far beyond the technical expertise honed in his academic pursuits. He is also a writer with a true passion for science education and outreach. This passion is evident not only in his impressive bibliography of 3 published books, but also in his ongoing projects settled for release later this year and early next. Notably, Mr. Varun has consistently chosen to offer his seminars free of charge, demonstrating a commendable dedication to making knowledge accessible to all. Mr. Varun's current professional endeavors are equally impressive. He serves as a managing director of the Aviakul Group of Companies, a forward-thinking initiative with a bold vision to revolutionize the entire commercial aviation and aerospace ecosystem within India. This commitment to progress extends to his role as co-founder of the Center for Scientific Outreach, a non-profit organization dedicated to bridging the gap between scientific advancement and the public through engaging outreach activities. Please join me in giving a very warm welcome to Mr. Vaibhav Varun. We are eager to hear his insights on the intriguing topic of calculus and the delicate balance between intuition and rigor within this field. Over to you, sir. Thank you.
Thank you so much, Vimal sir. And I'm honored to be here at the discussion today. So again, sir has given the introduction, but I'll quickly add on a couple of things. So the topic that I chose today is called Calculus, a retrospective view on intuition and rigor. Now, whenever I speak, I like to simplify my words, especially when I use big words. So when I'm talking about the word retrospective, it simply means to sum up past events. And then it's added with 2 other jargon words called intuition and rigor. Right. Now, intuition, as most of you might know, it's about something that looks obvious to us. So, बहुत simply दिखता हो. And for the audience, I would like to say that anytime I'm not clear or you're not understanding me, you can raise your hands on Zoom and I would be more than happy to clarify what I'm saying. And rigor, by the way, is where we spend most of our time in mathematics. You know, by rigor, I mean algebraic expressions, trying to prove things out of the formulas that we have learned right from class 6 all the way to till we do our BSc, MSc. So most of our time is spent in rigor, right? And somewhere in the journey of rigor, the intuition goes away. So that is what I'm going to talk about. Obviously, it's not possible to talk about calculus in 45 minutes or 1 hour. It takes years and years of understanding. But I'll try to sum up whatever I have understood about calculus in short 45 minutes. Especially trying to put intuition and rigor into picture together, right? Again, I'm not going to be talking about history too much. You can read about it online. My focus will be to understand what calculus really is and on what legs it stands on, right? So we'll go ahead. I think most of you have joined. And once again, thank you for having me here. Thank you for the participants who joined in, right? So I'll start out. I have, as most of you might know, I've written a small book. It's called the Calculus Experience. So for most of the lecture, I would like to share that book as a reference whenever I would speak something. I hope my screen is visible to everybody. Is it?
Yes.
Second, you confirm? Yeah. Okay.
Yes, sir.
Perfect. Perfect. Great. So I'm just gonna start right off here. Right now, first of all, coming to the word calculus itself. Now, literally, it just means pebbles, right? Hindi में बोलेंगे पत्थर. Right? Calculus का मतलब सिर्फ पत्थर होता है. And what has Pathar got to do with anything what we are studying right here? Because for calculus, we are given very big promises when we enter this subject. It's been told that it's the language of universe, and that's how the change happens. It's the language of change. जो एक बहुत आजकल प्रचलित शब्द है कैलकुलस के साथ कि कैलकुलस इज द लैंग्वेज ऑफ चेंज, राइट? तो यहाँ पे दो चीजें आती हैं. नंबर वन, what is language got to do with mathematics, and how does change come with a word that is associated with pebbles, right? It's literally meaning pebbles. Now, one of the biggest things that I learned very late in my life is to not treat mathematics as a subject, right? So when you go to a certain country, it's always preferable if you know the local language. If you're going to Germany, you would like to speak German. If you're going to Japan, you would like to speak Japanese, right? So it's always said that if you speak the local language, it makes your job easier. Now, when we are trying to study physical sciences, when we are trying to study the nature, it is said through our years and years of experimentation and studying that there is a certain language in which the nature likes to speak. Although, if I may consider the situation outside, I'm in New Delhi right now. It's raining heavily. There's thunders, there's rainfall, there's different kind of sounds. And all of this sounds very chaotic. It doesn't feel like there is an order to it. But somehow we believe that amongst all this chaos and disorder, nature likes to follow a pattern. Right? How do we discover this pattern? That's again the branch of science, what we call as physics, and we go deeper into the kind of patterns that nature follows, right? And we somehow try to figure out some sort of intricate thread that binds all this order and chaos together. And when we are trying to understand this chaos, we see that underlying all these chaotic activities is some sort of pattern, right? And all these discussions, all this thousands of years of history of mathematics and sciences bring down to us to something called as the mathematical language, right? So we settle down कि nature ये type का language बोलती है, and we are still discovering, we are still trying to understand how nature behaves and what is the language it is trying to speak. Now in mathematics, for our convenience, we have chosen our own symbols. For example, one symbol that you see right here is the symbol of infinity. I hope everybody is able to see. I'll zoom in if it's not visible right here, right? It's called the 1 by infinity that you see. Now, infinity in itself, we have chosen a symbol. And from our childhood, we have been taught different kinds of symbols. There is plus, there is minus, there is addition, subtraction, differentiation, integration, all those kind of symbols. These symbols are merely something called as just letters of these language. So just to give you a small example, a wise man told me long back that there are three things which are almost identical, but people don't look at them in that identical way. Number one is mathematics, number two is chess, and number three is music. Now, I haven't come across somebody who's good in all three. I'm certainly not me, of course. Now, if I were to talk about chess and music, keeping maths apart for 5 minutes, how does chess work? You've got two sides, and you assume that the pawns on the board of the chessboard act like soldiers, they act like king, they act like queen, somebody acts like horse, for example. It is important to understand that there is no real soldier, or there is no real king standing there. There is no real politics happening on the chessboard. It's all in the mind, right? So the number one assumption of the game that we have made is that each of these pieces and I've written about it in my book also. I will try to somehow go to that. Yeah, so it's just right here, chess, math, and music that I've seen. It's a game of strategy, as chess is a game that came out of India. And as I was saying, we just assume that all of these pieces lying on the board of chess are actually king, they are queen, somebody is a horse, somebody is soldier, whatever. And to each of these pieces, we have allocated some kind of rule. For example, the soldier shall move 2 steps when the game is being started. It will move only 1 step in the forward direction thereafter, right? So there's some set of rule that we have made, and the entire game is played according to those number of rules. Now, once we are clear with these kind of rules, we go ahead and we strategize. We try to predict what happens when our opponent plays a certain move, and then we are supposed to respond. And that is where the strategy making comes into the play. The same goes for the idea of music. No, music is there. Anybody who cannot even understand the complexities of music, they can still enjoy any good piece of art, right? But if you look at music closely, we have notes. In English, they call it as ABCD. In Hindi, they have Sare Gama Pa. So when you have a certain note, you assume it with a certain kind of frequency, certain kind of sound. You combine different kind of notes together to make a piece of music. And therein, when you write music, it's just symbols. So they don't really stand for some kind of sound, but it's just a symbolic representation of how a music would feel to your ears. Now, in between this, there's a journey. Not everybody can actually translate a good piece of music to the notations that is kept on the plate where you read the music. But somehow translating those notes written on the paper, when it is played, it plays a certain kind of melody. And in fact, that is true for all sources of mathematics that we have. We have made up some kind of symbols. When you say in algebra, you have x, y, z as some letters. In calculus, we use different symbols. We have d by dx, we have integration, we have limits, whatnot. These limits are given an assumption. They stand for something, right? And after that, we set up the rules of the game. For example, one rule that we have been taught right from the childhood is that you shall not divide by 0, right? Now, why this rule exists, nobody knows. We don't dedicate enough time with our students of class, because it's typically at this stage when you're learning division, right? You learn how to divide 1 by 2, then you go into fractions, then you extend that into decimals and whatnot. And therein, all our teachers, all our instructors, they give us this holy rule of mathematics that you shall not divide by 0. And that for me is somewhere the beginning of calculus. That is where we should have actually started teaching calculus at that stage. When we tell people that thou shall not divide by 0. Now, why shouldn't I? So I'm going to start my whole talk on this topic. I'll go forward to that particular page right here. Okay, so let's, 2 more words to be clear. I'll add annotation if it's, I hope whatever I'm writing should be visible now. Vimalji, if you could just confirm what I'm writing is visible.
Yes, sir. It is visible.
Perfect. So I will again, as I always do in all my classes, I would like to make my words clear first of all. I have 2 typical words that I keep using. There's a word called indeterminate versus there's a word called not defined, right? And I'm sure most of you, whatever your level of mathematics or sciences, whatever class you're studying, you must have come across these 2 words now and then, right? I'll start with the word called not defined. So once we enter with something called natural numbers, right? And we give a definition to each symbol. We write 1, 2, 3, 4, 5, 6, and whatnot, right? And we have given particular definition to these kind of numbers. So when we say 1, you can represent on your hand what 1 is, what 2 is, what 3 is, and so forth and so forth. There is a particular definition to these numbers. They are defined, as we to say. Then we extend our number system, we add a 0, and 0 becomes a little bit tricky to understand because nothing, there is no picture. कुछ नहीं क्या होता है, कुछ नहीं से आप कैसे add करोगे, कुछ नहीं से आप divide कैसे करोगे, and things start getting trickier. And then we put, negative numbers. We put -3, -2, -1, whatever. But we still have some kind of picture. They are defined. Once you say take a number scale and you say that 0 is the origin, and you know that if I say +1, I'm going to be moving towards right and I come here. If I say -1, I'll end up here. So there's some kind of definition to what you're saying. Once you say that, look, I'm going to do 2 into 3, for example, and the result is 6, and you know that you will be taking 3 things together and added together, they will give you 6. So there is some kind of definition. We know what we are talking about. Once we divide also, let's say we have 4 and we divide by 2, we know that we get 2 as a result because there will be 2 parts of 4 which make up 2, for example. So in all these situations, we have something called as a definition of each thing put into place. And all these definitions, they fall apart when we put 0 into the picture. And I will again reiterate what I'm going to say once I delete all of these things that I've written. So let's say a typical mathematical problem that I'm dealing with in division, which is little bit not so intuitive, and again use the word intuitive, is that if I were to divide a certain number by 0, right? Now, on the onset, it's very difficult to even imagine what I mean. What is the meaning when I say that I divide something by 0? So let's say I divide something by 2, and I know I have to split something in 2 parts. So I've got one slice of pizza, and I write here 1 by 2, and I know I'm going to end up with half and half of pizza here. It's pretty defined. Right? Similarly, when I do 1 by 3rd, 1 by 4th, 1 by 5th, 1 by 10th, makes sense, right? I divide by smaller number, I know how to divide. So I divide by half, and I know that the answer will be 1 by 2, which according to the rules of division gives me 2, for example. But what exactly is the meaning of dividing by 0, which is the root of calculus, as I told you? Dividing by 0 rigorously would make sense, as the word rigor implies. Intuitively, it doesn't make sense because we cannot picture. To think for 5 minutes, sit back and try to understand how does somebody divide by 0? Does it even give you any result? And can we even divide by 0? For example, we have been told that what teachers tell us in class that if you divide by 0, you get infinity. But what is the meaning of all those things, right? So we'll just look at try to get a feel of what nothingness is, right? And as I write here that if you divide something by 2, you get half. You take a smaller number, you divide by half, you get 2. You divide by 0.1, you get 10. You divide by 0.01, you get 100. You divide by 0.0001, you get 10,000, for example. And suddenly you start noticing a pattern that as you divide by a small number on the denominator, so you take as small number as you feel like, and you keep getting a bigger number. You've seen that the numbers here are getting big. It's 10, it's 100, it's 10,000, and here is, I don't know, some billion, and so forth and so forth. It's a pattern that we have observed. And similarly, I might want to ask you a question. What is the smallest number that you can divide? The smallest number. Now the definition, there is no definition of the smallest number. Like, what's the smallest number? So typically we have been taught that 0 is the smallest, but still we don't have a picture of 0. But going by this pattern, which loosely translates that if I divide 1 by a very, very small positive number, I will get a very, very large positive number, right? And similarly, if I divide 1 by a very, very small negative number, I will get a very, very large negative number. Now, if you look at the statements I'm making, these are not very hard, rigorous statements, because what is the meaning of very small? Right? The word very is very subjective, right? You can say that 0.01 is small. I might not agree with you. I might say 0.001 is small. And then you say, okay, divide by 10 again, you get a smaller number. So you can keep on getting between 0 and 1. You can have as many small numbers as you feel like if you want to call them small, for example. And the same goes for the right-hand side. When I talk about what is the big number that I'm getting, and really I can get as big of a number as I can feel like. If you say 1 billion is a big number, I can add 1 and I can still get a bigger number. So there's no limit to what is the biggest number that I can think of. But I do somehow see a pattern that I can get as big of a number that I would feel like. Okay. And then I would just, yeah, okay, fair enough. So I will just go to the next. Okay. Perfect. So just a second. Okay. So coming back, as I told you, we have 1 by a small number, or rather, let's make it more interesting, a very small number. Now, this word very is very subjective. Like, what do I mean by very? There's no picture. I happen to get a very big number. So symbolically, this very big number is what we have denoted by this symbol called infinity, right? And infinity, as you can understand, it's not a number that I'm talking about. 1, 2, 3, 4, 5, 6, 100, 200, 1 million, 1 billion. They can be numbers. Infinity cannot really be a number. Right? It cannot be a number because we are basically just saying a big number, right? And that number can be as big as we feel like. And therein lies the very basic generic problem of calculus and mathematics that I would say that now we have our whole life. If you look at what we study from class 4th to class 10th, for example, we have been accustomed to deal in very hard facts. You know, x square will be this. X square means x into x. If you look at a plus b the whole square, for example, you will get very hard results, and so on and so on. So we've been taught to think in very hard facts. The word that I use here is hard facts. कि ऐसा ही होगा. And now suddenly we take the most basic operation of mathematics, which is division, and we go away from that hard fact. Because infinity is not a hard fact; it's a concept. It cannot be defined, right? So once we say, for example, 1 by 0, which, by the way, one thing that you note here, that I'm using a couple of symbols here. I'm using, if I were to translate into words, I would write 1 divided by 0 is infinity. That's what it means if I were to take symbolism into picture. But I'm not really dividing. I never divided by 0, but I somehow write for the sake of symbolism. Just for the sake of writing something, I write here that I have divided by 0, wherein I still don't know how I could divide by 0. I have merely concluded that if I go on dividing by a very small number, and I know that the smallest number that I think of is 0, for example, on the middle scale, I will get a big number. So to say that this mathematical symbolism is not a hard fact, but it is merely a translation of a language into symbolism, right? That infinity is a concept that. So one thing to understand here is it's quite evident that it's a huge number, but there is no definition to how huge it is. And therein I use my word called not defined, right? Wherein it means I know what the answer will be. So I have some idea of what the answer could be. The answer is a big number. I divided 1 by a very small positive number. I get a very big positive number. What is that number? I cannot define. But the crucial thing to know is that I know the answer. And that's where things start getting more tricky. I know the answer, I cannot define. Like when you divide 1 by 2, you know the answer is 0.5 and you can define what 0.5 is. But you cannot define what infinity is, right? And therein, I have given you the definition of the word that I'll be using again and again in this lecture. It's called not defined, right? Let me look at a very interesting another word that I had used before this, which is essentially called as indeterminate. Now, this is more tricky, right? At least in not defined, we were just saying that we don't know. We have not defined the answer, but we know the answer, right? But at least we know the answer, right? Let's talk about a situation where I were to divide 0 by 0, right? And things start getting more interesting. So let me distribute this into two parts, wherein I divide some number by 0, right? And as we had discussed, we saw one example where we were dividing 1 by 0, and we got a very big number, which is what we are calling as infinity, for example. That is case number 1. Case number 2, when I divide some other numbers, for example, 0 by some other number, some number. So let's say I divide 0 by 2, 0 by 3, 0 by 4, for example. And in all cases, the answer happens to be 0. This is what we have been taught. So now you see in one case, when 0 is in denominator, I get a big number. When 0 is in numerator, I get 0 as answer. So now the question is, when 0 is in both numerator and denominator, should I get 0 or should I get infinity? And herein, I have no way of finding this answer. There is no answer to this question, right? And that is why I use the word indeterminate. Determinate, which can be determined. Indeterminate, which can never be determined. Now, if you cannot determine, how will you resolve that situation? That's a very central part of the problem here. That at least in the not defined situation, I was knowing what the answer is. It's just that given my limited knowledge, I'm not able to define. It's fair enough. But I end up with a situation where I'm not even being able to determine what the answer is, right? And this is one of the cases that I have told you, being 0 by 0, for example. If I were to look at some other cases, for example, I'll go to next slide right here, right? So, for example, as I told you here, Yeah, one beautiful proof that I forgot to take up here. You can see the bottom of the slide right here, wherein just for the sake of adventure, we wrote that 1 by 0 is infinity, as I write it here. And if I were to follow the strict rules of mathematics, I can just take it here and I can write 0 multiplied by infinity is 1, which I don't even know if that makes sense in that case. And I can just write, for example, that 0 can be written as 2 multiplied by 0, for example, into infinity. And I can write as 2 into, sorry, 2 into 0 into infinity. And I know from here that this basically equals 1. So I can just write 1 equal 2, and which makes no sense. How can you even say that 1 and 2 are equal? Because they're both defined. We know what 1 is, we know what 2 is, and they're certainly not equal. So this is what happens when you apply the basic rule of mathematics into things which don't have definition, which have not been defined and are not determinate either. Right? So weird things come out of, because this breaks our intuition. Again, I can go back to the word intuition, because by intuition, I know that 1 is not equal to 2, but somehow this set of operations is getting me to the results where 1 is equal to 2. So, and that certainly we know intuitively that is not possible. And that is where the trick lies in terms of the indeterminate situations, that it will give you things that you cannot possibly divide. And that's what I've written here, that I mentioned a few moments ago that you should be happy that at least you have an answer in the not defined case, because here you cannot even determine anything close to an answer. And that's what we call as an indeterminate case. And the sad part is that all of calculus, whenever we go into calculus, even before going into calculus, we must understand that all of calculus is basically, and that I write it here, that entire calculus is to know how to deal with this indeterminate forms. And I again repeat my statement. The whole goal of calculus would be to know how to deal with this indeterminate forms. For example, coming back to the pictures, we define speed as distance by time, right? It's the most basic thing you learn in class 6 and 7. And now I question you that if I were to travel 1 kilometers, for example, in 1 hour of time, or let's say for the sake of argument, 60 kilometers in 1 hour of time, and you say that my speed is 60 kilometer per hour, but that's only average speed. What do I mean by average speed? I might not be going 60 kilometer per hour at every instant of my journey in that 1 hour. So I might be needing more accurate measurements. How do you do more accurate measurements? You say, okay, let me not measure in 1 hour. Let me measure in the gap of 30 minutes, for example. And I might have traveled some distance, let's say according to this rule, 30 kilometer, for example. And even then, the answer is still 60 kilometer per hour as average. But it does not prove that I was always going at that result. Or you could have a situation where you travel some number in 30 minutes and some number in 30 minutes. So for example, you traveled only 20 kilometers in 30 minutes, but you traveled 40 kilometers in the next 30 minutes, you still end up getting 60 kilometer per hour as your average speed, right? And that's not the true representation of how you got this number. So the only way to deal with this situation is you try to take small measurements of distance and you try to divide it by small gaps of time, right? Now the question again is, since I started my lecture, is that how small, right? How small can the distance be? As small as you like. You can go to 0.1 meters, you can go to 0.01 meters, you can go to 0.0001 meter, and so forth. Next question, how small gap of a time? You can take 0.1 seconds, you can take 0.01 second, and as small as you feel like. But if you were to find the exact speed at a certain instant, you would like the time to be as small as possible and consequently the distance as small as possible. Now, what is the smallest you can go? You can go 0 by 0, and therein you're stuck. You're stuck with the same problem that we were discussing before, that this situation is indeterminate. You cannot determine this situation. It's not possible. and you're stuck, right? So this is where the hard problem of calculus lies, that all our problems lie into somehow knowing how to solve 0 by 0, but we don't know how to solve 0 by 0. We have discovered certain techniques that will give us some kind of accurate answer, but we will never ever know exactly what is 0 by 0, because this situation does not make any sense at all. Another example that I would like to give you is when we are trying to calculate areas, for example, right? Now, we have defined just by ourselves that when you take a rectangle, the area happens to be length into breadth. Now, I would like you to stop for a moment and think that why we have made all our formulas, all our equations, calculations in terms of straight lines. Just a historical notation, right? We always like to think about things in straight lines. Something that has been historically, if you look at the plots that you have in your field, they're always square plots or rectangular plots and so forth. We are not very comfortable with dividing plots like this, for example. But nature is not like that. Nature is not going to listen to us. Nature doesn't say that just because humans have made notations in straight lines, let us move in straight lines. And you see that in nature, rarely something happens in straight lines. If you see the flow of river, it's very random. If you see how thunder comes up, it branches out, for example. So rarely something happens in straight lines in nature. So naturally, when I'm talking about measurement of areas or measurement of anything, it's a very less chance that I will end up with shapes which are purely in terms of straight lines, as in to say, in terms of square, it is very simple, neat and clean drawing that if this is A and A, you have the area as A square, for example. If you have rectangle, as I mentioned, it's length into breadth. And this is something that we have just invented for the sake of our comfort. We like to think, because when we have a big figure, for example, when we have a triangle and we divide, we think of it as a half of a rectangle or a parallelogram. So it's just our notation. That's how we've been teaching to children. When we write the area of a rectangle, a triangle, for example, let's say this is length and this is breadth, we like to imagine that somehow this is half of a bigger rectangle, wherein the length was L and B. And because this area was L and B, this triangle is half of this L and B. And we say that the area of this triangle is half of L and B. And that's how all these formulations came. But later on, when we try to go to a more complicated case, right, as in to say, let's say that I've got some kind of curve like this, and I would like to again find the area of this curve. What is this curve that I'm talking about, for example, right? Or I take a circle, for that matter, right? And I have to somehow find the area of the circle. How do I do it? The natural instinct is to somehow go back to straight lines. That is our entire problem. When we introduce the number pi to children, we call it as 3.14 and so forth and so forth. And we define it as the circumference divided by the diameter, right? How do you exactly measure the circumference, for example? Or how do you exactly measure this area? The immediate intuitive solution is to divide this shape into as many rectangles as you feel like. You keep on dividing it into rectangles. And therein you see that you have some gap left here. You have this little gap which is left. You see here, there's a little gap this is left. So we see that although we have divided it into some sort of collection of rectangles, we have some gaps. And the only way to cover these gaps is to make smaller rectangles as small as possible. That is to say that you would like this width to be near 0. And if you make it near 0, you would have many, many rectangles that exist. You will not have a finite number of rectangles. Again, I end up in a situation where I'm forced to multiply 0 and infinity, where this happened to be the width and this happens to be the length, for example, right? And again, this happens to be indeterminate situation. So both the classical cases that I have observed, wherein people like to call it as derivative or differential calculus, and they say that, okay, you have small change by small change, for example. And this situation means that you would like to get closer to 0. And this would also mean that you would like to get closer to 0, compared to what we call as integral calculus, wherein you are given a situation like this, where one thing happens to be as small as possible, and the second thing is as big as possible. And both of these situations end up in a word that I call as, or the mathematicians call as, indeterminate, right? If it is indeterminate, how is there a solution? And that's where, for most of the students, the word intuition breaks down. No, it goes away. And rigor takes over. Because now we have no picture of what's happening. We don't know how to multiply by infinity. We don't know how to divide by zeros, for example. We don't know how to divide 0 by 0. And that is why the topic of the lecture, as I mentioned, is a retrospective view on intuition versus rigor. That intuition and rigor, as I say. As you go deeper into calculus, somehow the intuitive pictures start breaking down and the rigor takes over. But the beauty is, as this rigor takes over, the results that it is trying to explain are more and more intuitive. And this I would like to take in with my last example of what happens in a circle, right? And this is one wonderful question that I give to everybody. Just get back to. Yeah, okay, perfect. So this is about your famous letter pi, right? And I always happen to ask people that instead of pi being an irrational number as 3.14, whatever, if pi was just 3, for example, just 3, a neat, nice number 3, how would our world change? Right? How would the world that we view changes? So let me just get back to the story. As I mentioned here, exactly, yeah. So I mentioned this question here. How would the illustration 3.1, how would your handwriting change if you lived in a universe where pi is equal to 3 instead of pi is equal to 3.145, whatever it is, right? Now let's see. We have defined a notation called a k, that is basically the perimeter of the shape divided by the longest diagonal. So in case of you having a square, you know that your side is a and your diagonal is root 2a. If you were to judge how big the diagonal is compared to the side, you will have 4a is the perimeter divided by root 2a, which gives you a number 2.82 whatever. The same you can do it for an octagon, because octagon has got 8 sides. You know the diagonal of octagon, and you have this number 3.06 whatever. You can take a decagon, where you can have the perimeter of a decagon as 10a, and you know the diagonal as whatever 1 plus root 5a, and you get a number 3.09 whatever. Interesting observation. As you increase the number of sides, you see that for the shape starts approaching a limiting value of 3 point something something. You started with 2.8, then it went to 3.06, and then this 3 stopped changing, it went to 0.9, whatever, right? Now, the next big question, what would this k be for a circle? Now, the most problematic thing about a circle is we don't know the number of sides it has, and we would just say that the perimeter in a circle essentially means the circumference. Right? That's how you have defined circumference. So for a circle, the perimeter circumference, and the longest diagonal that you call any side would be the radius, right here. So typically, this k for a circle would basically mean that you're dividing this, I'm sorry, not radius, but the whole diameter, right? Circumference divided by the diameter. Now, what do we do for a circle? Number one problem, we don't know the number of sides that a circle has. So again, we use the word infinity. We just think that circle is a shape that has got infinite sides. We cannot count the number of sides. So you have a shape where the circumference is basically you have a polygon of infinite sides divided by the diameter. And that number somehow gets you to this value of pi, which is 3.1415. And so this ratio refers to the curvature of the shape that you're talking. It's as simple as that. So in reality, in nature, for the curve to exist, pi is the very foundation. And that is why it is infinite in nature. That's why we can never find a ending value of pi. It has to keep going on forever because it is ratio of two things which can never end. You can never ever have a polygon with infinite sides, and thereby you can never ever reach to this exact ratio. We can be as close to a circle as we would feel like, but we can never really be a circle. So that is where, again, as I said in calculus, your intuition will break down and your rigor starts to take over right in the very nature of pi. And therein is an interesting number called E also, which I don't have time to talk about. But you get a fair idea about how pi lies. Now, again, emphasizing, we should not just think of pi as a number. Pi is a symbolization of, it's a symbolic value of something that represents curvature in nature. If you were to have a shape with infinite number of sides which keep on changing, you keep on going to that idea, right? And as in mathematics, in the word rigor, we say this whole thing as limits. That's what we call in the language of rigors, that we go to a limit where we are able to imagine something having infinite sides, although it does not exist, it can never exist, but is there in nature, right? You would get a number called pi, which will give you a shape with a curvature of infinite sides, right? And you have seen the number pi coming quite frequently in mathematics, quite frequently in physics, for example. All these ideas, and again, that's how I conclude my lecture. Begin with things that have very simple meanings. Go to things which look simpler. And suddenly, when you think that you have resolved the problem, they get you to things like 1 divided by 0, 0 divided by 0, infinite divided by 0, 1 to the power of infinite. Wherein things start breaking down, you don't have numbers. And that is precisely why calculus took something like 2000 years to develop. Because for a good part of this 2000 years, we were busy struggling with the chaos or the difficulty in understanding the concept of what happens when you divide something infinity by infinity. And I sum up all of calculus into this two very basic problems. And it's everything about trying to multiply 0 with infinity and trying to divide 0 by 0 in very bare minimum terms. Of course, I made it too simple, and if they are teachers, they would be laughing at this idea because calculus is not as easy as I have summed it over. But just to give you a playground of intuition and rigor, this is where we stand. This is where we keep up our problem statement that if we were to know how to manage to divide 0 by 0, and if you could somehow find the intuitive picture of how do you multiply 0 by infinity, and that's precisely what Newton did. He said, leave intuition, let's not imagine. If the math works, if I have a fair idea, if I have an approximate idea, I'm happy with that. So I conclude my lecture with this. I've been given exactly 45 minutes, and I think I've made a fair justification to it. So I'm open to Q&A from the audience. I hope you were able to make out what I was able to say. My language is clear, and thanks a lot.
Okay, so we have a Q&A session now.
Yes, please. Yeah. Yeah, in fact, you can post your question in chats also. I might be able to read chats. Okay. Can we have another session on number E? Yeah, definitely. I mean, time allows. Why not? Vimal sir, please. आप कराएंगे तो हो जाएगा.
जी बिल्कुल सर.
E is another interesting journey. And I would actually like to add something here. I recently worked in a movie. It's called All India Rank. It's about journey of students when they go to Kota. And for that movie, the director told me that you have to teach pi, E, calculus to the actors, right? And it is very difficult. I'm assuming that most of my audience here understands mathematics, so it's easier for me to talk. But imagine when I talk to actors and they don't know anything, they have no picture of what 0 is, what infinity is. So therein I realized that it is possible to explain calculus without going too much into rigor. Rigor is for classroom, and that's the whole idea of having these webinars, that we are outside the classroom. Yes.
Right.
So there's another question by Tharmishta Sahu. If 0 and infinity are defined, how do you conclude that 0 is a very, very small and infinity? So that's what I told. I would like to make correction here. Infinity is not defined. That's what I mentioned in my lecture. if I were to actually define, I just know what infinity is intuitively, बहुत बड़ा होगा. But I cannot really put a definition to infinity, and that's why they are not defined it. So 0 is pretty much defined, but infinity, I don't think we can put a definition. Okay, and if we are approximating pi to 3, are we approximating pi to hexagon? That's exactly what I said. If you are taking pi as 3, you are basically talking about a special case in which our world is just hexagon and everything will not be able. So that is to say, if I were to write it, annotate here, if I write something like my name for it, if I write calculus, the word C, you see has got infinite curvature here. If my world was just pi equals to 3, I would just write C as a part of hexagon. I cannot do any curvature more than this because I've been limited to pi equals 3. It's as simple as that. Yeah, okay, another question. So instead of us defining pi, it is something that is defined rule in nature. Exactly, that's what I meant. Language of nature. It's a number that nature has given. We have not. We have merely discovered what pi is. We have not invented pi. Again, so can we say some infinity are smaller? Yeah, that's how, because can we say some infinity are smaller or bigger than other infinity? Yes, that's a central statement in mathematics, that we say that some infinities are bigger than another infinities. Quite possible. Okay, sir, in which field we will be having calculus? Calculus pretty much is a branch of mathematics, but I think you will enjoy calculus more in physics. That's what I feel like. Sir, could you please tell your journey in mathematics and physics? Very long answer, but I would definitely say that I was not a very good mathematics student. Physics थोड़ी बहुत समझ आती भी थी, mathematics तो बहुत कम समझ में आती थी. Although my father is a gold medalist in mathematics, but I couldn't really understand mathematics. The reason is it's very abstract in nature, and I again use the word called abstract. What is the meaning of abstract? Like chess, but at least chess में एक board तो है. Okay, you can see what is happening. Mathematics, after a point, is just symbols and symbols. So you're not really getting a picture of what is happening with those symbols. हम एक rule के according इनको move तो कर रहे हैं, but what is the meaning of those symbols? It becomes very abstract, right? So that's why it took me some time, but with time I did catch up. Sir, in future, can we define infinity? I mean, yeah, some, I don't know, because utni mathematics मुझे आती नहीं है. If some mathematician comes around who can define infinity, why not? Sir, is there a way to state pi is irrational without explicitly using calculus? Like, suppose calculus hasn't been developed much, but I do have definition for the number k we defined above. Can I still state on nature of pi? Yeah, I think yes, because the very fact that you can never ever have a shape with infinite sides, it directly implies that this constant k will be a never-ending number, because you can still get something on the farthest side of decimal. It is irrational if you want to purely define it by intuitive way, not by rigorously. Rigorously, no. Intuitively, yes. Quite possible. Sir, if 1 by 0 equals infinity, then we prove that the question, we can say 1 equals 2 and so the question is, if 1 by 0 is infinity, then we proved on the question that we can say 1 is equal to 2 is equal to 3 is equal to 4, and we take any digit. Does that disprove everything in math? That's the problem I started out with, that if that was possible, we would have disproved everything in math. But because it is not possible, because we don't know how to define this, that is why mathematics is stable. We are at a stable state in mathematics. Sir, why, sir, after any number, if there is a decimal, that can we neglect it and take only one number so that it gives approx calculation? Depends on what you're solving. I mean, आपके problem statement पे depend करता है. If you feel that approximation to one digit is okay, then if anything multiplied by 0 is 0, then why isn't 0 into infinity is also 0? That's precisely, again, it is one of the indeterminate case that I couldn't discuss due to lack of time here, but I think I did discuss. Sir, would 0 more of a number? What is it? 1 second. Sir, would 0 more of be a number or mere symbol of? I couldn't understand this question if you were to reframe. I'll go to another question, sir. So if our intuitive conclusion that 1 by 0 turns out not equal to infinity, then it would also imply that similar approximation for pi being maximum curvature is incorrect. See, again, it's an intuitive conclusion. That's the foundation of maths and physics, and so far, whatever we have implied it on practical applications, it has given us right results. So I'm assuming at this stage of mathematics, this intuition is correct. But just for the sake of argument, if you say it is not correct, then yes, pi being the approximation for maximum curvature is not correct. Then that case. Okay, so how do principles of calculus answer variables? Very interesting very interesting question. How do the principles of calculus, particularly the concepts of limits, enhance our ability to grasp how functions behave and tackle practical challenges in the real world? Right now, the good thing about the real world is when things get too small, at least in our real life. For example, when we are doing, a carpenter comes, when he is hitting the nail on the wall, he also knows that no matter how the nail goes, however the nail is close to the wall, it is not really into the wall. This is what the exact theoretical implication of calculus is, or mathematics is in general, for example, right? But for all practical purposes, as long as it is holding something, we don't really care, right? And there's another paradox which was shown that if the distance between two people is x, and every time I travel half the distance, the next time I go 1/4 the distance, the next time I go 1/8 of the distance, I will never be really close. But for practical purposes, if you're 1/16th meter away from me, I can still touch you, right? So practical world is like that. Thank you so much, sir. Loved the session. I'm glad you loved the session. Sir, why is something, sir, as any number divided by same number is 1. So 0 divided by 0 is not 1. Again, as I told you, for 0 being divided by 0, for any number being divided by same number, right? So when you divide 2 by 2, you are not just saying same number by same number. Remember that we are saying same number, right? Infinity is not number. Similarly, when you say 0, can you really call it a number? For the sake of simplicity, we have called it as a number. In your question itself, you have said number by number. I wouldn't really consider 0 by 0 to be a case of number by number. Yeah, that's the last question I see here in the chat. Okay. Sir, will the evaluation of 0 to the power 0 also produce a similar intuitive conflict? Yeah, pretty much. In fact, if I were to go back, I'll just show you the kind of non-intuitive cases that we are dealing with. Just a second. Yeah, so as you can see in the screen, I think I have, yeah, you have these kind of the 7 indeterminate cases, right? So another question that it says here is, sir, you told that dividing 1 with very small positive value gives a very big value, and when this value tends to 0 gives infinite. But what if we approach from left? Yeah, it also goes to a very big negative number. By negative means on the other side of the 0. So it's still big on the other side. But infinity on other sides, if that's the meaning you're. Sir, in mathematics, we treat 0 more as a number or a symbol. I think most situations we treat it as a symbol. We just don't say that we are treating it as a symbol. Hi, sir. It was an awesome session. We met at Sopan Ashram. I too love and wish to pursue aeronautics. My question is, how are infinities, different sizes included in calculus? It's to be honest, I cannot answer this question in 5 minutes. I need a 30-minute session for this. Okay. Any more questions? I think pretty much all. Vimal sir, I think we don't have any more questions here.
Okay, sir.
Just see if there's more questions, I'm ready to answer. No worries.
Vaibhavji, I would like to ask you a question.
Yes, ma'am. If I'm able to answer, I'll answer.
No, it's a very easy question. Just
Yes, ma'am.
popped up. When I have a circle, I can measure the circumference of the circle.
Yeah.
Let's say I use a thread,
Yeah.
and I can measure the circumference of the circle using a thread. I would say to a certain approximation.
Yes.
Also, I can measure the diameter of the circle.
Yeah.
Again, I mean, to a certain approximation, I can do that. So both are kind of fixed values.
Exactly.
The circumference is a sort of a fixed value. the diameter is also a sort of a fixed value.
Exactly.
But the ratio,
Yeah.
interestingly, is
Yeah.
not fixed.
Yeah,
That is a very, very
yeah. So here, ma'am, the basic flaw in this kind of measurement is that although you're talking about a circle, you're using a thread to measure, which in any situation is a straight line at the end of the day. So you have again approximated your answer with the usage of a straight line, which is what my initial proposal was, that we always go back to straight lines. And in straight lines, we get exact answers. But I don't think any circle can be approximated by measurement of straight lines.
But then it was I mean a flexible thread. I
Yeah.
made it a straight line later
Exactly,
on.
exactly.
Later
Exactly. But
on,
when you join the thread together
and yeah.
in this joining, and therein lies this entire gap will decide everything, because you can never be precise on the joining of this circumference.
Okay.
Yeah.
Interesting.
That's what because I had the similar question, but the idea is that ultimately we define circle to be a polygon that's infinite number of sides. So I cannot possibly go into that kind of accuracy. I cannot be accurate to infinite number of decimals if that's the answer you're looking at.
Okay. Thank you for your answer. And it was really a pleasure to hear you. Thank you
Thank
so
you so
much.
much, ma'am. Thank you so much, ma'am. I hope there was some fruitful information for the children.
Sure, it was.
Yeah. Perfect, perfect. So I'll close my session here, ma'am. Thank you so much for having me here.
Thank you.
Perfect.
Vimalji, if I think he would want
Yeah,
to.
sure, sure.
Yes, ma'am. So, esteemed guests and dear friends, as we wrap up this insightful webinar, I want to express our deepest gratitude to everyone who helped make it a success, especially our esteemed guest speaker, Mr. Vaibhav Varun. His presentation was truly eye-opening, calling all the curious minds. Did you know the National Anveshika Experimental Skill Test 2024 registration is open? This is your chance to dive deeper into the amazing world of physics and explore your scientific potential. Don't miss out. Registration closes on May 20th, 2024. NAST is more than just a competition. It is a thrilling adventure. This platform allows students to showcase their knowledge, skills, and creativity in the realm of experimental physics. It is a chance to ignite your curiosity, unleash your innovative spirit, and push the boundaries of scientific exploration. We encourage everyone to consider joining NAST 2024. Share this exciting opportunity with your friends and classmates. Participating allows you to not only gain valuable experience and recognition, but also contribute to the advancement of scientific knowledge. NAST is a journey of discovery and growth. It is challenges you to think critically, solve problems creatively, and collaborate effectively. Skills that are essential in any field, not just science. So take this incredible opportunity, expand your horizons, deepen your understanding of physics, and connect with other science enthusiasts like yourself. Together, let's embark on this journey of exploration of and discovery, pushing the boundaries of knowledge and innovation even further. A final thank you. Once again, our deepest gratitude to Mr. Varun for his enlightening presentation. To all our participants, thank you for your engagement. Let's continue to inspire and support each other as we strive for excellence in the world of physics and beyond. Thank you, everyone.
Thank you. Thank you so much.